Hello everybody, welcome back to another video, and in this video we'll be looking at the integral of cosine of ln x. And in this video we'll be using two methods, and the first method is the more traditional way to approach this integral, and the next method will be using some complex analysis. So let's get started. So we have the integral now of the cosine of ln x. So what we can do is we can take a u sub and we can say u is ln x. So with our u subs, we need to take the du, but what we can also see is that solving for x, we know that e to the ln x is the same thing as x, and that's a key fact that we'll be using in our video, and I'll just make a note of that. We know that e to the ln x is equal to x. So what we can see here is that if we raise both sides to the power of e, we'll see that this and this cancel. We see that x is equal to e to the u. So now, very easily, we can just take dx to be now e to the u du, because we know the integral of, or the derivative of e to the u is just e to the u, but then because of the chain rule, we multiply by the derivative of u, which is du. And then what we see here is we can take our integral to the u world. So we have now, this is equal to the integral, and then cosine of ln x, and our ln x is our u, so we have cosine of u. And guess what our dx is? Our dx is just e to the u du. So we have cosine u multiplied by e to the u du. And that is our integral. And this is a pretty cool and a case of a repeating integral. This is a standard integral if you're taking like a calculus 2 course and learning about integration techniques. And for this, we have a product of two functions. We'll need to use integration by parts. So what we can do is we can set you can use the DI setup, and then in the DI setup, it's the same thing as integration by parts. It's just a more visual way of setting it up. So what we do is you have a D here, and you have a plus, minus, and that should be good for now, and you have an I. And of course, D is what we're going to differentiate. So let's say we're differentiating the cosine of u. Of course, remember this is in the u world, so that is totally fine. And let's integrate e to the u. And e to the u is easy to integrate or take the derivative of either way. So anyways, let's compute the derivative of cosine u now. What we do, derivative of cosine we know is negative sine of u, and integral of e to the u is e to the u, and then we can just do this again. And what we see, the derivative of negative sine of u, well, we know the derivative of sine of u is the cosine of u, but we have a negative there, so then therefore this must be the negative cosine of u. And when using the DI setup, what we do is we take the product of the diagonals and the last row as an integral. So we take this multiplied by this as a first part of our answer, and this multiplied by this. And of course, these signs need to be applied to each function here. And then the last row is an integral, and that is the product of the last row. So what you see here is that realistically, this part right here is just an integral. So that is the case in every last row in the DI setup, no matter how many rows you have. So what we can see now, our first part is now the cosine of u multiplied by e to the u. Then the next thing we have a minus multiplied by a minus sine of u multiplied by e to the u. Well, we have a minus sine of e to the u, and taking the negative of that, that's going to cancel the negative. So we just have a plus now, a positive sine of u e to the u. And then finally, we have this integral right here, which is the product of the last row. Now, what we see here is that this is a positive. However, we have a negative cosine u here. So what we can see here is that this is the same thing as adding. Now, we have the integral of negative cosine u e to the u du. And what we see here is that we can take this negative sign out because this is a product, and we can replace our positive with a minus. So this is equal to the cosine of u multiplied by e to the u plus the sine of u multiplied by e to the u, and then minus the integral of cosine of u e to the u du. Now, this should become pretty clear because what we see here is that this is exactly what our original integral was. So let's say our original integral, let's say the integral that we have here, I, is equal to the integral, and what is the integral we're trying to compute here? It's cosine u e to the u. Cosine of u e to the u du. Well, that's just equal to all of this right here. So that is equal to the cosine of u e to the u plus the sine of u e to the u minus, and then what we have here is just another I, because this integral right here is exactly what we've defined to be I as. Now we can treat this as a regular equation that we can solve for. So what all we have to do here is that we see that we have I is equal to something which happens to be e to the u. Let's just factor that out now. Cosine u plus sine of u now, and then minus another I. So what we can do is that we can add an I on both sides and then solve for I. So we add an I on both sides and we see that 2I is equal to e to the u, and then we have cosine of u plus the sine of u. And then finally, to solve for I, of course, we divide both sides by 2. We see that this cancels, and we see that I, which is equal to the integral of cosine of u e to the u du, is simply just equal to, now let's distribute this e to the u once again, e to the u cosine of u plus e to the u sine of u, and of course everything is divided by 2. Now the final step we need to take is we need to bring this back to the x world, because remember, our original integral was the integral of cosine of ln x. So let's just make a note here. We know that x, so we know that our u was ln x and our x was e to the u. So all we need to do is we need to bring our integral back to the x world. So we finally see that the integral of the cosine of ln x dx is equal to, and here e to the u right here we know is exactly our x, and that goes for the same thing here. So what we see is we have x cosine, and then what is our u? Our u is ln x, so cosine of ln x. Then what we have here, we have another e to the u, so that's an x, and then we have a sine of u, so let's just move this over. We have x sine of u, so we have a sine, our u is our ln x, so what we have here, sine of ln x. And finally, we are done. We divide all of that by 2, and we can put a plus c, and see that we are done with this integral. However, there is a much cooler way, and I will show you the second way of looking at this. So let's just make a note. This is the first method of going about this, which is the more traditional way and standard way. And the second way involves complex analysis. So what we need to see is that the first fact that in our video that brought us to this u substitution, the fact that e to the ln x is equal to x. So let's just write this here. We want to evaluate the integral of cosine of ln x. And what we'll be able to do using this method is not only evaluate this, but evaluate the integral of sine of ln x. So we'll essentially kill 2 birds with 1 stone. So what we can see here is that we know that Euler's identity states that e to the I theta is equal to cosine theta plus I sine theta. And we've worked with this a lot in my previous videos. And now what we can also see is that we can write the some x power raised to the I. So wait, before we do that, let's just look at something more simple. Let's look at 2 to the I. How do we take 2 to the I power? Because we have a complex exponent, so how do we deal with that? So to deal with that, what we see is that 2, which can be our x here, is the same thing as e to the ln 2 as stated by this property here. So what we can see here is that 2 to the I is the same thing as e to the ln 2, all raised to the I power. Now, given that our base is real and we have an exponent and an exponent on the outside, and the inner exponent is in a bracket, then what we can do is we can safely multiply the exponent. So 2 to the I is just equal to e to the I ln 2. Now what we see here is that this is in perfect form for Euler's identity, and this is something that I covered in one of my previous videos, this exact example. This is just more of a speed run of it. So what we see here is that we have e to the I theta is cosine theta plus I sine theta. Here we have e to the I ln 2. So therefore our theta must be equal to ln 2. So therefore we see 2 to the I is equal to, now using the expansion, we have cosine of theta, which is ln of 2, plus I sine of theta, which is ln of 2. So what we can see here is that we can generalize this into having some x power, because what we want to do essentially is to reach the cosine of ln x using Euler's formula. And what we see here is that to have an ln x, our base must be of x. And we see that x to the I now is equal to e to the ln x all raised to the ith power, which is equal to e to the I ln x. And using the expansion Euler's formula, that's equal to the cosine of ln x plus the I sine of the natural log of x. So this is essentially it. We have just found the key to solving our problem, because what we do is we can actually apply real and imaginary operators. So for instance, this piece, this expression right here, if we take the real part of this expression here, what we see here is that if we take the real part of this expression, this will return the cosine of ln x. And if we of course take the imaginary part of that expression, so let's just paste this again. If we take the imaginary part, that should return the sine of ln x, because the imaginary part is the part where the coefficient is an I, or it's being multiplied by a term of I. So what we need to do is we need to see that we're trying to compute the integral of cosine of ln x, and that happens to be the real part of x to the I. So if we take the integral of x to the I and we take the real part of that, we're essentially doing the same thing. This is essentially equal to the integral of the real part of x to the I. Now what we can actually do, which is a cool property, is we can take this real part out, because just a recap, so x to the I expands to this term right here, and taking the real part we get cosine of ln x, which is exactly what we're integrating. So what we can do is we can take out this real part and out of this integral, and you see that we get the real part of the integral of x to the I dx. So what this is essentially saying is once we compute the integral of x to the I dx, taking the real part of that resulting expression will give us the integral of cosine of ln x. So that is pretty cool. And we can also logically see that if you take now the imaginary part of this integral, that would return the integral of sine of ln x. And that's what I meant by killing two birds by one stone, because with this you can also compute the integral of sine of ln x, and we'll see how that works later on. So what we can do now, computing the integral of x to the I, we have an indefinite integral, and we don't have any need for any sort of paths or any sort of complex integration techniques. We can just treat the I as a regular constant. It is the imaginary unit, the square root of -1, so we can just use the power rule. So this is, I'll make a note here, the real part of, and then, well, what is our favorite power rule? X to the n plus 1 over n plus 1. Of course, given that the original n is not -1, but now we see that here we have x to the I plus 1, and then let's just write this like x to the I plus 1 multiplied by 1 over the new power I plus 1. So how do we work with this? Because taking the real part of this is not so clear, because we seems like we have complex parts in both terms. So what we can do here is we can use the property that we know that I is the square root of -1. So therefore, I squared is -1. So if we multiply this expression by the conjugate, then we should end up with something a lot simpler. So this is now equal to the real part of x to the I plus 1 multiplied by, and then here we are multiplying by, let's just make a note here, we're multiplying by, and then what is the conjugate of that? Well, that's 1, or I minus 1 over I minus 1. So what we can see is, yeah, this should be fine. So we have an I minus 1 over an I, so we know that the multiplying by the conjugate means that we have a difference of two squares. So we have a squared minus b squared is a plus b times a minus b. So here we have a squared, which is I squared, minus b, which is 1 squared. So that is what we have here. We see that now this is equal to, now this entire integral is equal to the real part of x to the I plus 1 multiplied by I minus 1 over I squared is -1 1 squared is 1. Negative 1 minus 1 is negative 2. And I just realized that I used a different color there, but it's all good. And what we can do is we can take this negative, because this negative is multiplying this whole expression to the numerator. And what we can do is this, when this negative is on the numerator, we can distribute the negative to each term and see that we get now, using that same color just to continue now, x to the I plus 1 multiplied by, and we have now distributing the negative. Negative of I minus 1 is 1 minus I, so we get 1 minus I, and that negative from the denominator was used for precisely that, so we just have an over 2 here. And what we can see now is that we need to use the idea once again that x is e to the ln x, and we see that this identity is very useful. And what we can now see is that this is equal to the real part of, and then x is e to the ln x, and that's all raised to the I plus 1 power, and that's multiplied by, and then let's just write this in this color now, 1 minus I over 2. Now, what we can also do is we can multiply the exponents once again using the same idea. This is real part, just an index file, real part of, and then we have e to the ln x, and then what do we see? We have an ln x multiplied by I plus 1. So distribute this to distribute the ln x to each term in this bracket. We have e to the ln x multiplied by I plus, and then ln x times 1 is ln x. And that's multiplied by 1 minus I over 2. Now, the second thing we see is that we can use, again, one of our index laws, the fact that if we have some a to the n multiplied by a to the m, that's a to the n plus m. So what we can do is we can use the reverse of this idea to break this exponent down. So we have the real part now of the expression e to the ln x. I'll write this as I ln x. And then multiplying now using the reverse idea of e to the ln x times, once again, 1 minus I over 2. And what we see here is that e to the ln x, well, of course, that is just x. So we have now the real part of e to the I ln x multiplied by x times 1 minus I over 2. You can write it like this. And what we can see now is that e to the I ln x, well, that is what we looked at earlier. That is just the Euler's formula. We can use the Euler's formula on this to get cosine ln x plus I sine ln x. So this now is all coming to the real part of, and we see that now we have the cosine of ln x, because of e to the I theta, cosine theta plus I sine theta. So cosine of ln x plus the I sine of ln x, and I'll write this purposefully multiplied by, and then I'll write this as 1 minus I all multiplied by x over 2, because of course that is the same thing, the laws of multiplication. We can just swap the order around with this number system. So what we can now do is we can just take these terms together, and we can see that, let's just put a bracket around this to be more precise. This is the real part of, now what we can do is we can just distribute these two binomials and see that this is a term where we just multiply out the brackets, and we'll leave this x over 2 as it is, because we see that we have something nice there that is a real part. So what we have here is we have now, let's do this off to the side. So we have cosine of ln x plus I sine of the natural log of x, and that is multiplied by 1 minus I, like so. So first thing, we take this multiplied by that, so this is equal to the cosine of ln x, and then next thing, we take this multiplied by that, so we have minus the I times the cosine of ln x. Now we take this multiplied by that, so plus the I sine of ln x, and then finally we take this multiplied by this. Now what we need to consider here is that we have plus I times minus I, and what we see here, I squared is negative 1, but when we have I times minus I, that is minus I squared. I squared is negative 1, so we have minus of negative 1, which is just a positive 1, so these actually cancel out to just a positive 1 multiplied by sine of ln x, so plus just a sine of ln x. So you can make a note of that, I times minus I, or more precisely writing this is minus I times I is equal to minus I squared. And remember that this minus I is not in brackets, so minus I squared, that's equal to minus of -1, which is 1. So finally here, we can take this part, and we have the real part of this entire expression, and then all of that, remember, is still multiplied by the x over 2. So we have this entire thing. Let's just make this a bit smaller, and then that multiplied by x over 2, and that is the closed bracket. So let's continue from there. So let's continue like that. So now we have the real part, and let us actually now write this. Let's group the real parts and the imaginary parts. So what we have here, this is a real part, so I'll write this with this color. This is a real part, and this is a real part, as we can see, and this is an imaginary part, and this is an imaginary part. So what we can do is we can write this as now the cosine of ln of x plus the sine of the ln of x, and then plus, now we have a plus, so we can do this, and then what we see here, as these are both imaginary parts, we have an I which we can factor out, and then we have, of course, sine of ln x, because we have this minus this, it doesn't matter which way you see it, so we have the sine of ln x minus the cosine of ln of x, like so, and we have to still see that. Let's just fit in this x over 2 over here and close both of these brackets. So finally, after absolutely everything, we see that we have the real part of now distributing this x over 2, that's pretty easy. We just have now x over 2 times the cosine of ln of x plus the sine of the ln of x, and then we have now the I multiplied by, and then we can write this as x over 2 times the sine of ln x minus x over, or let's just keep it like this. So we have two pairs of brackets here minus the cosine of ln of x. Just getting a bit crammed here. And now we see that our original thing is we're taking the real part of this entire expression. And what we see here very nicely, we have an expression in the form of a plus bi, believe it or not, which is the standard form of a complex number. And when you take the real part of some complex number a plus bi, that's equal to just a. And that a real part is this part right here. And the imaginary part would be this part right here. So what we finally see is that the integral of the cosine of ln x dx is just equal to the real part of that entire expression, which comes to x over 2 multiplied by, and then let's just actually distribute the bracket. So we have an x cosine of ln x plus the, and then we have an x sine of ln of x all over 2 plus c. Now you may be saying, well, this took much longer, or took even longer than the first method. Well, to that I have to say that this is a much cooler method, and what we also see is that we actually got the other integral, which is the sine of ln x as well. So that is an added benefit of using this method, is now we see that while taking the imaginary part, that is now distributing the x once again, we have x sine of ln x, and then minus x cosine of ln x all over 2. Once again, put a plus c there as well. We can box this as well. So we have successfully used complex analysis to evaluate two tricky integrals. So, and we can of course double check with our first answer to see that they are the same, and therefore of course this part must also be correct. So that was it for today's video, and thank you for watching.